Welcome back, everybody, to another exhilarating episode of Energy Bites. Rad Dad here, John Calfan. Bobby is out today. It is the last Friday of school before Christmas, and so I think pretty much every school district in town has a half day. So he's playing dad this afternoon. So it's just gonna be me today. But today I've got Scott Paper. Got Scott, our field CTO at Ansys. Thanks for joining us today, man.
John, thanks for having me. And thanks for the warning about traffic when I leave here today. There's going to be a little bit more traffic, I guess.
Oh, man. I mean, I actually posted it on Twitter. I always put in work on my Google or Apple CarPlay this morning when I come in, and it was only 17 minutes from Katie. And I was like, oh, wow, perfect. Miracles do happen. Yeah, that's normally
gotta love Waze.
30, 45 minute commute time. So you've definitely got 980 Fridays that you can definitely tell where traffic slows down, but then you've got kids not going to school today as well. So that's going to be a good one. Well, good. Appreciate you coming on. You've got a really cool kind of history experience career-wise and stuff. And so I kind of want to jump in on both mechanical engineers, but kind of tell us, how you got into the energy and or tech space, kind of going up to where you're at today at Ansys.
Sure. Well, look, engineering is one of those things I think you discover it quite young. I was always quite curious about how things worked, and I had a habit of taking things apart. Not necessarily all the screws came back in when I put the toaster back or the air popper, but it was that kind of a childhood, right? You always kind of, which led me more to the mechanical side, only because I did an experiment with electricity. It didn't work out very well, and I said, that may be a little too dangerous for me. So anyway, I ended up in mechanical engineering, and then really because, of that curiosity and how things worked. And then to be honest with you, my favorite topic in college and high school was really physics.
Yeah.
And so as much as I didn't go into electrical engineering, I really was curious about how everything worked, electromagnetics and so forth. Material science was very interesting. So I kind of fell into it that way. And I think it affected my curiosity in science and engineering for my entire career. So even as I became a CTO at whether it was GE, BP, or Baker Hughes in different roles, I stayed very curious technically. And I'm not saying I could go deep with each of all these PhDs and scientists, but especially in technology development, I found it to be, and you and I talked a little bit about this before, I found it to be very enlightening in terms of where that tech may end up globally in a product space. I mean, you think glass is not that interesting. Bulletproof glass gets more interesting, and glass that can be used as a solar panel is even more interesting, right? So even something is maybe as simple as that can evolve into products all over the world. So that kind of curiosity to me was what led me into engineering. And I started with an undergraduate degree and then realized, or at least my professor made me believe, after doing a summer internship at a paper mill with Bechtel in Maine, I realized I wanted to be on the design side, not the field installation side. And he said, "Look, you
didn't enjoy your time at the paper mill."
Well, the paper mills can be quite dangerous. They're not as dangerous as they used to be.
They really are.
They used to be one of the more dangerous industries.
No, for sure. Yeah. The amount of mechanical engineers specifically that I know that have worked at a paper mill in some form or fashion is pretty crazy, actually.
Yeah, it is. It is.
And none of them work at paper mills because of that experience.
Well, I am from Maine, so paper mills are important, but to the economy up there. But ultimately, there was a, it became more and more automated too. They were one of those industries where they became, because of the hazards, looked at automation differently. It wasn't just about pennies saved on the pound. It was about pounds saved on the body. Yeah. And so I think that always made paper industry. But I, after that, went to graduate school at Penn State, did my master's degree in aerospace engineering, and started using, frankly, the Ansys product. Started doing computational work in acoustics and structural mechanics and vibration, space thrust dynamics, and these kinds of things. And I thought I would end up, looking at satellites when I was done. Instead, really, end up working for companies like GE. At the time, aerospace was a little bit in a slump. This was late, early 90s. So I ended up in automation, in robotics for compact disc and DVD manufacturing, which dates me. I mean, that stamps me pretty good in terms of tech.
But that's a fascinating time, though, right?
Yeah,
because
it was because we didn't then have tools, and we didn't have the connectivity.
Yeah.
But what was interesting about our equipment is because they were all automated, we did have all the sensing and equipment in one place. So that one brain, real time, we could do a lot of things.
Yeah.
It was quite interesting.
Well, even from like a product perspective, right? Like, man, I'm going to forget the name of that book, but there's a really good product book out there. And again, I'll remember that probably at the end, and I'll put it in the show notes, but he talks a lot about like, it's about the evolution of products and how they, like, generally speaking, will spin out of a major, like, why can't, the whole thesis of the book is why can't these giant GE style companies, or, you know, IBM back in the day, why can't those companies innovate as quick or as fast as like the new companies and stuff? And one of the examples they use in the book is they were talking about like early days of computer storage with the hard drives, right? And so like, you know, whoever it was, C-Disk or one of those old school players, you know, they were highly focused on just making the desktop computer hard drives smaller, more efficient, etc. Well, in that project, this small group of guys developed this really small hard drive. It couldn't store as much, but it was very performant and low power consumption. Seagate didn't want it, or whoever it was. I don't remember, but they spun off a company that then started targeting the new laptop market, which, you know, was still very young, and a lot of people didn't know what that was going to be. And then they, you know, step change jumped their prior company, started their own company because they didn't want anything to do with it. And now they got bought back, you know, 10 years later from that company. Right. And so even like in that space, like I remember back then, right, we went from the OG floppy disks to hard floppy disks to CDs. And then I remember wanting a zip drive so bad just because of the storage capacity, right? Like you could go, I don't even remember what it was.
I don't know if any company would let you use a zip drive because they think you're going to take the data home with you. And they're probably, you know, so it's funny how you say that. I mean, technologies get adopted and then obsoleted.
Well, yeah, like HD DVD is another one, right? Like the whole Blu-ray DVD, HD DVD kind of saga, right?
All of that.
It's always fascinating to see that, like, over time, how all that plays out and why one wins over the other and all of those different kind of knobs that turn. So,
and I actually, that would be one of the things that from a career standpoint, really helped me define where I would go next, because I realized that in this very small company, you know, when I joined, it was like 20 of us. When I left, I was running it, and about 300 of us. But at the end of the day, that company came and went with the tech.
Right.
And, you know, we tried to leverage it into other kind of and it just didn't work. And I think one of the things I learned in going to GE was, if you're in all these spaces, first of all, the pace and into your description in terms of how do you move quicker in the innovation space. Sometimes you got to carve people out and let them focus. And other times you've got to give them the support that only a scaling large company can give them, not just financial support, but maybe it's manufacturing know-how, lean know-how, whatever it might be, to help them move more assuredly with less risk. That's still going to have risk in maybe the tech and or the development of the product, or the market isn't ready. But you have the leverage of scale in terms of how you get there with some level of confidence that you're going to make it.
Yeah, no, that's like, I think that's probably one of the most interesting dynamics in like the energy tech space specifically, right? Is you've got, you know, every startup looks at all the big publicly traded companies and they're like, you've got all the resources in the world. How come you can't innovate faster? Or how come you don't want to adopt our new thing or technology or whatever? And then the flip side of that is it's like, you've got all this innovation and you can move very quickly, but you don't have those processes and structures to go scale, to manufacture, to support. Like, big companies do certain things very well. That's why they got so big, right? But smaller companies do the other thing really well, but then they can't, you know, there's that dichotomy of them where it's like them trying to bring a product to market is very different at a small startup than at a GE or a IBM, or a big, huge
Well, you're
monolith.
really working on profitability, different sides of that curve,
you know?
And it's kind of interesting. You know, I had a couple of stints where I ran and operate like a COO role, and I had manufacturing and engineering together. And I remember I reported both to the senior leader of engineering at GE and the senior leader of manufacturing at GE at one point. And in those conversations, you know, they were typically not together when we had, so I would talk to one guy one day and the next guy. And I remember the manufacturing leader said, listen, we can't overthink this. We're knuckle draggers. And I stopped the mid-sentence and said, don't ever call me a knuckle dragger, because there isn't any role in any big company where you shouldn't be. And I look in good faith. He was a good friend of mine. So it was not, he didn't mean it as an insult. But the reality is, a lot of times the opportunity to innovate is in the white space between functions still today. We see, a lot of verticalized, and we decentralized engineering in most companies. I don't know whether it was which of the consultancy companies told everybody to do that 10 years ago, but it almost killed innovation because now we've taken engineers that used to work collectively together and we've separated them all and put them in little boxes and said, don't talk to each other, right? So moving around the cabin and in manufacturing at a company like GE or any of the other large industrial companies is in fact, a science around how do we get this product safely and quality control and all those things you probably don't have to worry as much about. It's like when you're patching a software that, is showing you how to do TikTok dances. I mean, that isn't even comparable to the level of safety, right? And we thank God that we have in the big industrial space. So it does change. And I think a lot of those small companies, wide-eyed, pretty bright, but at the same time, don't understand that piece. Yeah. You have to live through a product failure at scale, at the hundreds of millions of dollars of scale. Hopefully you don't have too many of those in your career, but when you do, it changes the way you think about that stage gate design process and why it's so important to get as much as on the table early and tested and verified before you ship. But those are different business models.
For sure.
Yeah.
Well, tell me, because like I said, so you've got a very kind of interesting background both on the energy tech and product space, but what are some things, that you see companies do well, so to continue this conversation on, right? A lot of times what happens is those smaller players, they innovate, they move fast, they have something unique, proprietary, et cetera, and then they get bought by, a large publicly traded, whether that be, on the oilfield services side, like a Halliburton, Schlumberger, Baker, or, on the industrial manufacturing side, whether that be GE, IBM, whoever, right? Like they get bought, and sometimes those companies buy them and then that technology goes to die. Yeah. A lot of in some of these companies, like notoriously. And then in other companies, they're actually incredibly good, even like with oil and gas operator MMA or M&A, right? Like when Exxon bought XTO, right? Like XTO kept their office and they allowed them to operate as two separate companies, but with the support of and the resources of the big company instead of forcing the innovative little company that we bought because they were innovative and they had a new thing or they had a different approach, and then forcing that into, the monolith archaic, or not archaic, but just rigid structure of a super major type thing. Right. Yeah. So what are some things you've seen people do well as far as that, either with product or, acquisition, or what are some areas where you've seen like very common mistakes that, you might not think?
Yeah. I've lived through both of them. Right. Yeah. So I've been acquired and many times my small startup company was acquired by a German company. And that first run of that experience was, a German company came in and said, okay, who's running engineering? You run the company. It was almost that stark kind of a decision. And, processes were what they were. We were a much more, what we'd say, kind of a Western startup. Now we weren't a West Coast startup. We were an East Coast startup. And the difference is you didn't know if you were getting paid that week, right? Today, it's a little different. These guys get big series of funding. But anyway, from that standpoint, having been acquired by a German company, very similar at the time, I think, when Daimler and Chrysler were getting together, and I was reading about some of the cultural issues, we were a much smaller company. And yet at the same time going through a lot of that same cultural issues. So to me, it comes down to people. John. And I've been on the acquiring where I'm doing the acquiring, or been part of whether it's GE or Baker Hughes, where we've acquired companies in the energy space specifically. And we've recognized that financially, the mothership can't afford to have a compliance issue there, right? So that quickly gets lined up. HR then follows that same stretch.
HR is right behind
for kind of the same reason, and at the same time, where some of these companies, the leadership and the understanding who knows what becomes important. So HR and finance typically very quickly, I support that. I think when you get down to the next level, specifically in engineering and the science space, I think there's way too many folks who don't have enough experience to know what they're doing in terms of how quickly they're crushing innovation. And it's hard to see sometimes. I mean, it depends where you come out of engineering. Yeah. You come out of field services, you come from a research institution, and I don't think there's any right answer there. But what I would say, what I do see works well, is some level of recognizing we bought this company for a value. Let's let the engineering teams in let's say the mothership. I'll keep calling it the mothership. Get some experience with that tech,
right?
And you will find usually a great balance of floating some people across into that company for the right reasons.
Right.
Not to be there to be
Right.
knuckle whacker.
The dictator and push everything down.
And I've done that a number of times. We bought a technology from when I was with General Electric in the clean coal gasification space here in Houston. And Exxon and Chevron would just kind of come together, and Chevron said, look, you can take this technology. And we thought clean coal was going to be the thing. At the time, natural gas was $15 a BTU, right? And so fracking wasn't even in the conversation at that time. And so General Electric, having gas and steam turbines, recognized if we could decarbonize coal,
right,
and at the coal's price point as a fuel, and we could use that syngas to turn gas turbines, we had a solution that would be unique in the market. When I came down, I inherited like 5 or 6 chemical engineers. And what's interesting about that was those chemical engineers really had never made anything.
Right.
They'd done heat mass balances. They understood the petrochemical processes, but they hadn't made anything.
Yeah.
And General Electric came in as a company that makes things, right? Big, heavy things. Anyway, one of the things we had to go do was a syngas cooler and a syngas reactor. And I remember bringing in people from GE Research. I brought a lot of young engineers in. That's a risk. So I brought in professors to coach them. And the topic very quickly became, how do we create algorithms for all of this empirical stuff that we've been doing for years that tells us we understand what's going to come out of the other end of the cooler after the reaction. But what do we have to do to design a cooler?
Yeah.
And the first strike at this thing was something the size of the Statue of Liberty that cost $50 million a piece. And we all just looked at each other and said, is that what we have to do? And, but that's a long story. But ultimately,
I can envision this in my head, right? Hey, you gave the engineers the constraints and the problem, and they solved it. Yep. They didn't pay attention to the budget or the feasibility of that solution.
First time, Pat. So, and this was going back to your startup piece. That to me worked. Because we brought in people that weren't just General Electric people. Right. And if we did, some of them were from the research center, so they were a little bit more open to experimenting and modeling or whatever it might be. But I thought, where you come in and you don't recognize people and culture, it's obviously a catastrophe. And those integration leaders are often, unfortunately, some companies pick people who are just ripe for a promotion versus somebody who's ripe for the hard work, because it's a lot of work. Yeah. It's like any other startup, right? So anyway, I think those are lessons learned for me. But I'm not shy. Ansys today buys, we were really a 50-year-old company, and we were about $1 billion maybe 5-8 years ago. We're about just over $2 billion company today. And we do a lot of acquisitions in the software space. And typically, we've done some in material science. We've done some in systems optimizations that are agnostic to any tool that you might be using. But what's really exciting is we typically recognize that it's a niche, right? It may be very, very small, maybe 10 physicists who have figured out a new way to model the tear of material, right? The cracking of it. And so that particular science is so valuable and so important in so many industries. We can provide that algorithm, a home that allows them to scale that business. And at the same time, we know what the value of that predictive crack is. Yeah. In so many industries. So I think with Ansys, we typically we acquire about one company a quarter in this acquisition space, and it's all in physics most often. We do a little platforming, but not really much. We do platforming where it makes sense for computational solutions. Right. But in those cases, and I've been connected to a few of those. We always stew around whether it should be a partnership. Right. Is it something we need to be, ownership of, or is it something that could just be a partnership with us? And that then leads us to leaving those people where they are and doing what they're doing and putting a very, very limited amount of, and again, mostly finance and HR kind of, I won't say auditing, but compliance and that kind of thing.
Yeah. No, I mean, it makes a lot of sense. Like, when you break it down like that, right? Like, people would be like, well, why is this $1 billion company buying these like super niche kind of focused things? But to your point, right? Like, metal cracking or materials cracking literally applies to every
Correct.
industry.
Corrosion.
Corrosion's another one, right? Like there's all these universalities that, like, yes, it's a very small subset of every single market, but it's of every single market. Therefore, it has broad appeal and applicability instead of hyper focusing on one niche that is only that thing,
right?
And then being like, well, how do we grow this? Right, like not having that visionary kind of mentality of like, hey, this is not only applicable here, because that happens all of the time, right?
Correct.
Across industry, where it's like, hey, we've got this really cool thing, we're going to go to market, and we're going to build this company around it, and it's like you can do that, but you can also, like, if you really want to build a huge company, understanding where those things apply outside of your expertise or industry can be such a huge.
Well, it's a value multiplier too, right? I mean, because if you're looking in one sector and you don't have access to these other sectors, you're in fact not getting the scale quick enough, and ultimately sometimes that's what kills these startups. But the other thing, I mean, just not to be too salesy, but what I was just remarked at when I joined Ansys, 93% customer approval rating.
Yeah.
And on the top 10 list of companies most liked to work for in the United States, it's really not that difficult to find people that want to come work for you. Right? That culture is a winning culture, but it's also a culture where our employees are very, very, I mean, it's very flat. Our CEO is very accessible, remarkably bright man, of course, as you would expect. But what's really nice is there's a lack of, I would say, politics.
Right.
And, having been in mostly heavy industrial businesses for, I would say 28 of my 34 years, working in a data software-ish, although most of our company is physicists or scientists before they're software engineers. But in that space, it's really, the whole place is curious.
Yeah.
All the time. The level of questioning and asking and learning. I've never had a role in all these big companies where I would have thousands of employees. Today I have none. And I am learning at a rate like I was in college.
Yeah.
And I think, depending, and again, this is kind of important too, because a lot of the companies we acquire in our space aren't pure software companies. And they are physicists. So they find a home here pretty quick. And I think, any M&A activity, you've got to make sure that culture piece.
Yeah.
If it's not the same, how is it different? And let's talk about it. Let's make sure that's on the table.
No, for sure. Yeah. I mean, I've worked with a number of companies, whether it was overseas developers or I worked for a French company for a while that did actually basin modeling, which is another.
Okay.
That's the only simulation professional experience that I have.
Okay.
But outside of all the stuff, I did in undergrad with all my SolidWorks and 3D modeling stuff, but even that, right? Like within the same company, just cultural differences from from their locations can be like a crazy thing. No less. Okay, now we have that within the company that we're buying, and now we're having to figure that out, and our company's culture on top of that kind of scenario. So it's a huge thing, right? Like even to like down to certain countries, just generally speaking, not that I want to make any generalizations, but like, super, and even with the personality types, right? Like engineers, like really highly technical engineers tend to be hard to get like information, like concise information out, just like me right now babbling on. We're not very concise, right? Mm-hmm. Like, and so being able to understand like the personality type and how they communicate and how to extract that information that you're trying to get out of them is a huge factor. And whether they have, like a lot of developers I've worked with historically, hard to get emotion out of some of them, right? And you're like, I have no idea if this person likes me or hates me, right? Like just completely impossible to read in some situations. But that culture piece, I completely agree with you, is like the foundation of a lot of that M&A and even partnerships, right? Like just being able to make that work, because if it doesn't, it
just innovation in general.
Yeah.
Right? If you just talk about innovation, people like to talk about diversity, and I'm a supporter of diverse workforces. But my slant on that from experience is, if you have a diverse workforce but they're not connected to each other,
right,
who cares?
Yeah,
there's no value. But what I've seen is when you have a global workforce and you do have differences of culture and behavior in terms of how people work and like to work, you can actually use that as a multiplier.
Yeah.
And I used the example earlier, the white space between functions. I mean, I can't say this enough. I go into companies and your engineering and manufacturing folks, the engineering leaders sitting over here and the manufacturing, I mean, those desks should be put together.
Right.
And even inside engineering.
Mm-hmm.
So when you go inside engineering, I tell people today, I think multi-physics simulation is being limited by organizational structures.
Yeah.
And people look at me, what do you mean by that? Well, I mean, you got a mechanical engineer who's working on this problem. And I'll give you an example. I won't tell what company, but we were working on an oxygen sensor. And we already had flow sensing and so forth, but we wanted to make it more accurate. And ultimately, we migrated to a hydrogen sensing, which is pretty small stuff, hydrogen. So you've got to have the sensitivity. We had never run a multi-physics model of the flow of, using computational flow dynamics with the electromagnetic field that was being created by the power supply.
Mm-hmm.
And the reason we hadn't done it is, first of all, we weren't a simulation first culture in that particular part of the business yet. But when I asked the folks, listen, before you go do any experiments, I want to see a model that basically describes how this system works. Our physicist, not mechanical engineer, quickly realized, oh, wait, we're getting interference here from the electromagnetic field. Long story short, the sensor turns out to be orders of magnitude better in the first pass because we've taken two different engineering disciplines, not forced them together, but recognized in the real world, physics doesn't care that you're a mechanical electrical engineer, right? These things don't separate themselves. We may try to from a system standpoint. Right. But anyway, I find that's true too in innovation. And I think one of the things that kind of a pet peeve of mine is early, I would say 2015 onward. And I don't know which consultancy company, I'm pretty sure I knew, but started talking about blueprints. And everywhere I'd go from Baker to BP and back to GE, everybody wanted to start to decentralize engineering.
Yep.
And I had this conversation with a number of the CEOs ahead of time. I said, would you decentralize finance? and they would say, well, no, we really? Okay, because everybody turns in a different spreadsheet on Friday, the closing day. How are you going to put all that together?
Right.
So of course you wouldn't. But engineering, when you break it up into bits, small bits, right? You take this one brilliant material scientist, and he was over there, let's say in Germany, and you've got a group here in the U.S. that's working on high temperature electronics for downhole tools.
Right.
Why aren't they talking?
Right.
Well, because he works for this guy and he works for this guy. It's amazing how innovation is stifled by poor leadership.
Yeah.
And I sit with a lot of CTOs just because Ansys has that reach. I mean, we've got 45,000 or more customers around the world, and almost anybody that makes anything is using. We're about 50% of the world's simulation market. And so when I sit with these CTOs, I ask them really basic questions. And it's not, look, if you're really good in digital, you're going to want to use simulation. It's not really that. It's what are your aspirations for innovation, your engineering workflows, how your engineers, what they do, how they think, how they behave. How do you want to accelerate that pace with digital? And, it surprises me sometimes that you'll get a CTO who really has no strategy. They may have 1,000, 2,000, 3 or more engineers, and they really don't have a strategy. And they want to chase productivity because that makes sense. And so I learn a lot from the different folks I meet with, and Ansys and we all try to kind of help as an advisor with 93% customer. Mm-hmm. We're kind of partners with almost everybody that we work with. And we guard their information and their data very carefully. But ultimately, we think we help them innovate better if we can partner with them in terms of getting more engineers on the table working together. Regardless of org structures, but org structures can be a problem, just like in M&A.
No, I mean, that's probably one of my biggest complaints about the oil and gas side of it, like out of the gate, right? To your point, you've got some of the most highly technical engineering staff in the world working at these companies.
Correct.
And then it's like, oh, well, there's the R&D group over here. There's the reservoir engineers over here. Also, if you're a reservoir engineer, now we're going to split you up by basin, because surely there are no lessons that we can learn from other basins or other fields and that we're working in as well. Also, production engineers, we're going to do the same thing with you. Completion, you're going to be over here, and drilling, you're going to be over here. And it's like, this is all part of the same product, which is a well, which is all tied to revenue, which is the oil coming out of that well. So the faster the oil comes out of that well, the faster we get a return on our investment, and the faster we can keep moving down the line. And yet that is such like a novel concept to most operators. And I think a lot of it comes from like the disconnect, going back to our earlier conversation, right? Like when I was as an intern doing industrial engineering and manufacturing, and everybody's focused on the problem. Like, you wouldn't go build a widget and go sit it on the shelf for 9 months and then go sell it. Like that's a very hard business plan and model. And that's exactly what we do in oil and gas, where it's like we go acquire an asset. Okay, we come up with all these plans and engineering, and then we drill it. And then by the time it starts producing, it's 9 months later. All of the money is due up front.
Right.
It's super expensive, super risk, all these things. And then hopefully we'll make money on it at the end. It's like, if you can accelerate the time to revenue, you accelerate your ROI. Like it's basic, basic math and just
no
business,
one
right?
steps on the gas when they're lost. So if you're lost and you feel your risk, and I say this a lot, but ultimately, I won't drive 5 miles in Houston. I won't even drive out of my neighborhood without putting Waze on.
Yeah,
and yet I can be in parts of the world, and everybody agrees. Okay, well that's interesting. Well, that's a model. Guys, that's a model. Pretty accurate. I mean, it had me here within 30 seconds, essentially, of when I left my house, 30 miles away through traffic and, accidents and toll booths. And so people believe confidently in those kinds of models to go base their, stepping on the gas. I find it's just remarkable. We have big customers, good customers like Cummins, a good customer of ours that I can speak to. That is their CTO is simulation first.
Yep.
And whether it's simulation first or we're going to do systems engineering or whatever that's going to be, what I find the hybrid organization that works really well is having a few people at a center of excellence, not a lot of people, because then it can become more of a researchy kind of, we're just going off and studying our naval. When in fact what we want to do is we still solve a problem and we want to be directionally doing this.
Yeah.
But if you want to put all your engineering leaders under business unit leaders, some of which are not technical at all, and you want to call yourself a technology company, and that business unit leader really can't fall over a soapbox and understand the difference between soap and acid, then you probably have the wrong structure. And ultimately, it's not that it will necessarily fail. It's the things you just described, but it's sub-optimized.
Right.
I mean, it's people sub-optimized. And this is in most technical companies, this is the most valuable group you've got in the room, and not allowing them. I mean, we'll have this discussion about, well, should we, get the chief engineers together once a year? Well, it's too expensive. And I'm like, what are you talking about? The finance guys just got back and I just did a 3-session with ice sculptures out there, wherever it was.
Yeah.
And of course they did, because we got to make our numbers. You've got to make your products work if you want to make your numbers, right? So I always find engineering, and unfortunately or fortunately, and I don't want to be too outspoken about it, but I think engineering leaders, and one CEO told me this. He said, "Look, engineering leaders need to push back more," and that's a fair. In fact, I'll share it with you because I have a lot of respect for him. Lorenzo Simonelli, who runs Baker Hughes.
Yeah.
You technical guys got it. You got to see at the table, use it, right? I mean, and so I think even if you have a group that doesn't know that, it's your job as a technical leader to say, look, we have to have this. We have to do it this way, or we need to be organized in a way that allows us to share.
Yeah.
And if that means you can do it because the business unit leaders are all lined up around the fact that technology is going to get together one afternoon on a Friday, have a few pizzas and look at technology together, and then you can make it work.
Yeah.
They don't have to be restructured, but I find that to be globally industry independent, the biggest thwart to innovation.
Yeah. No, I mean, it makes a ton of sense too. And like, you see it on the software side, you see it in so many of these different fields, right? Where it's like, oh, well, we'll hire a developer to do it. And it's like, okay, well, if you're deploying an enterprise ready software product, you need a back-end developer, you need an architect, you need a front-end developer, you probably need a database guy. You like, there's all these specialties that fall under that. And it's the exact same thing with engineering. And for whatever reason, not many people think about it that way, where it's like, hey, just because you're a petroleum engineer and I'm a mechanical engineer, that's actually a good thing if we're working together, because we bring completely different perspectives to the problem that will make it better because we're not thinking in the same box.
Yeah.
And like, that's another big issue, right?
But that's diversity, right?
Yeah.
I mean, that's where, and I do think, gender falls in that and other things fall in that too, because people think differently. They come from, but it's a zip code thing to me. And if people are from one area of the country and have gone to these types of schools, then you mix them. You mix them up a little bit, and you mix the scientists. And there's a good book. I'm going to forget the name. It's IDEO is the name of the company, and the writer, an amazing story about how he was doing innovation. And it's called the Innovation Handbook or something. I have to give it to you later. But the company is a San Francisco-based company, IDEO, and these guys had come out of Stanford Design School. And again, independent of whatever industry you were in, they gave examples of where when they would want to figure out why people have stopped fishing for the fishing reel company, they were all going down. They tell the story in the book. They take their scientist, their engineer, their fisherman, their psychologist, and they put that team together because they wanted this kind of very different kind of thing. And they sent them down to the lake to watch people fish.
Mm-hmm.
And it was a psychiatrist about 30 minutes in. He said, wait a minute, this isn't where the problem is. These guys are already fishing.
Right.
We need to go find out why people aren't fishing. We need to go to Walmart and see where they sell this stuff.
Right.
And so that diversity of thinking, to your point, is really exciting because a lot of times what we would do is if we had a good idea and we kind of quarterly look at it and say, geez, this is something we ought to put a patent on. It's that good. We would say, okay, well, wait a minute. If we think it's a good idea now, let's take the 4 guys that came up with the idea, let's put them in a room with a whole bunch of pizza and a bunch of other disciplines and let them go after this and ring fence this to make a better patent.
Yep.
Because if it doesn't cost you more to have a crappy patent than that good one, right? I mean, you're still going to pay lawyers and all these guys to go do the work. So that was one of those things, again, where diversity was critically important to getting not a couple guys that look like me going, that's an answer, let's go with it. And actually Ansys leverages that today because with simulation, you're able to put a bunch of different variables and run a number of, not one solution and done, but I can run thousands, tens of thousands of iterations parametrically on this design or that design.
And you can have different people in the team too, because they have different assumptions or inputs and all that. And it costs
you very little.
Right.
You're not building a physical model. It's not taking you a test cell. You're not building braking. You're not testing and tweaking. You're going in knowing it's this one or this one are 10 times better than the other 50. Which one is going to win? Well, this might be a little bit more expensive. This might be a little bit more reliable. Let's see how those things play out, right? That's a much more intelligent conversation, and it brings more people in the room.
Yeah. I remembered the name of the book I was talking about. It's called Innovator's Dilemma. You made me think about when you said Innovator's Handbook.
Yeah.
I knew it would happen. That's
okay. John, I'm glad it came back.
No, I completely agree because that's, like frac interference is a big kind of trend in the oil and gas space. And I mentioned to you at one point, the longest I've ever worked at any company, actually, I was working for this gauge company. And right when I started, there was a lot of work. People were it was beginning of kind of frac interference monitoring, right? So people throwing pressure gauges on these offset wells and just monitoring the pressure to see if they saw any pressure increases from the offsets. And I'm sitting there thinking, as a mechanical engineer, I'm like, I remember all the stress and strain and the brittleness, like all of that mechanical failure stuff from undergrad. And then I'm sitting here thinking, like, why has no one backed out? Like this is basic physics. It's a distributed load. I've got a well bore. It has got this much feet exposed to the rock itself in this cluster with this many perfs. I am putting this much force on that length of the well over here. I've got a microphone over here essentially, and I know the distance between them. So I should be able, it's velocity and it's just basic calculus, right? And I'm like, this is like physics 1 stuff that I did in undergrad. And yet no one in the oil field is thinking about it in that way at all, because they're so in the weeds of, well, the rock is heterogeneous and it changes and all that stuff. And it's like, at the end of the day, all the models don't care because it's nanodarcy rock anyway. It's just a brittle piece of rock, regardless of how heterogeneous it is or not. Like, that's the other part of a lot of engineers, right? Is like they get so in the weeds of it that they can't back out and be like, hey, their hardnesses or their brittlenesses are slightly different.
They're not
the
accepting
model,
of the accuracy, right? So there's a difference between the difference between discovery and I don't want to fall off this bridge, and versus I want to make it across the bridge in 20 minutes. Those are very different objectives. But I think, to your point, especially in material science, what we try to do is we work at sort of the micro scale very, very accurately, meso scale, and then sort of the macro scale in these problems. And maybe you come up with an equivalency based upon, you've done a couple of tests in that basin, you've characterized that material by doing just what you said back into it. We actually did that in my Oklahoma lab with Baker Hughes a few years back. And we started working commercially with customers and say, listen, this, I wouldn't put it there. I would move it, right, left, and effectively over time demonstrated, hey, this is a pretty dang good tool. This is giving us very quick runs, very quick what if scenarios. And to your point, the level of accuracy was more than good enough to make a dent in something that was getting no help that way.
Well, and it didn't have to be from like a reservoir model that had every single piece of rock perfectly mapped and all of that stuff, right? Like it's a block. It has these general properties. You put a force on it and you can see the response over here after whatever, right? And
that's what we call physics informed.
Yeah.
And we find, a lot of times folks say, well, we're going to do big data. And I said, look, first of all, you have to know the subject to know what data to collect. And I've heard many AI folks, the minute they lose credibility with me and anybody who's an OEM is when they said, oh, no, we just need enough data.
Yeah.
And the reality is these models are learning from failure. And you and I are not accepting failure at 32,000 feet. No. I'm sure they're not interested in being part of that experiment. And so, at the end of the day, what we think is we know and we demonstrated is that you know most of the physics. There is a couple of variables or even constants to those variables. And where you might have the problem is, in the nonlinearities. That's typically where your error, whether it's an experiment that you're doing or a simulation you're doing. So that's engineering know-how applied to a problem, recognizing that, I was sitting here at the nuclear summit, ARPA-E had one on nuclear heat. So using small modular reactors and or fusion for heat for cement, steel, refineries, and so forth, all these applications. And I'm sitting in the back of the room and I hear one of the, nuclear is very conservative, but these folks are using a lot of simulation, a lot of simulation. And I'm hearing somebody, one of the EPCs kind of say, well, we're going to scale up this heat exchanger 5 times. And nobody in the room blinked. And I said, and I wanted to get up in the back. This is a kid's show, so I don't want to, be using expletive, but I want to say, what don't we know about the physics on a heat exchanger for a gas to gas exchange? I mean, what are we now? If you're trying to, I don't know what you'd be trying to study. I mean, you want to study material science and corrosion, we can go there too. But I find that to be ridiculous. And not only is it going to be expensive and time consuming, but it's the lack of understanding that these methodologies have evolved.
Right.
They're sitting on platforms. They're running 10,000 times faster computational fluid dynamics today in many applications, whether it's combustion or aerodynamics, from where they were 10 years ago. So if you haven't touched some of those new methodologies, you're not going to get there fast enough. And I think, one of the things I see is organizationally that can be a stump too.
Right.
If you think about it, if you've broken up all those engineers and all those groups and they're not talking and some guy over in the corner figures out you can do it this way better and doesn't share it with everybody else, that idea goes from an interesting idea to not scalable.
Yeah. No, that's, my favorite companies to work with in the inner, or at least in the upstream space is, generally speaking, tend to be the companies that have some kind of it's not an innovation like how can we bring outside tech in. It's an internal innovation group that is focused on optimizing best practices from across all of the assets. Yeah. And that's how, like, that makes so much sense, right? Like, hey, these guys, why is, the Eagleford faster at our frac turnarounds and has less MPT than the Permian? Like, it's so basic. And again, it's like back to this industrial engineering mindset of like optimize everything, and as you optimize, distribute the learnings of that across the organization. What a novel concept.
Right? I mean, listen, 9/10 of the safety you get in the aviation space is because people have a checklist, a common checklist. Oh, you forgot to close the door,
right?
Or you forgot to fill the tank. And it irritates people when you're on a plane because you hear them say, well, we got a little something with the fuel gauge and tapping it doesn't seem to fix it. And I remember being on a flight from Boston to, I don't know where it was, maybe it was Pittsburgh. And, the person behind me is like, well, let's go anyway. And I'm like, are you serious? I mean, so at the end of the day, where did you come from?
Of all the places
Stop
to
feeding
have
that one
mentality.
drinks, right?
Yeah.
I mean, but at the end of the day, right, standard work, best practices, lean principles, these are fundamental, and I call them management.
Yeah.
I mean, you can say, well, I don't, I'm not, well, know enough to hire some of those people and make sure you're spreading them around the organization, because if you're not, you are absolutely not capitalizing on the scale opportunity. And that's what big companies should do well.
Right.
Right.
Yeah. That's their differentiator, right? They don't have the new innovative thing. They've got the scalability and distribution.
Well, should.
Right.
Yeah.
And resources.
Yeah. Right.
Well, so tell me a little bit more about, kind of Ansys and some of the tools you guys have that fit in kind of the energy space and how people use them, success stories, failures, et cetera.
Sure. Well, I mean, so from wind, it was kind of the talk about the energy space. So when I think of the energy space, and I have to correct people, my own team sometime, it's everything from upstream, midstream, downstream. It's inclusive of the OEMs, the gas turbines, wind turbines, steam turbines, whatever it might be that's rotating, or the solar cell or whatever. And now that it's including things like storage and batteries and so forth. So when I think of energy systems, an integrated energy system,
all the way down to the electronics too,
all the way down to the circuit board,
yeah.
right? So where our tools are being used, and you think about high temperature electronics for downhole drilling. I mean, all of our tools, we are best in class in the semi space, and we'd probably surprise folks that even with a few customers in the semi space, and you and I were talking a little bit about this without getting into calling people out, because it is what it is. But because we are 50% of the simulation market, we kind of have a view of where companies are. And and you can digest this one for a second. The largest energy customer, not including the Department of Energy, the largest energy customer usage of simulation, hang on to your hats, is 1/30 the size of an average company in semiconductor that's using our product, or aerospace.
Right.
1/30 the spend. And we go in many times, and where I'm talking to somebody across the table who's going to go do a bunch of experiments, they're going to spend 10, 20, $30 million, and they've convinced their boss that's the way. Oh, of course, we're going to go spend 20. We have to spend the money on testing.
Right.
And when we come in and say, look, it's going to be, $500,000 in software, and somebody swallows hard, I look at the cross table and I just, oh my God, you folks, you're decades behind.
Yep.
So, in the energy space, we provide products from that are used in all those other industries too, right? So computational fluid dynamics that you would use for everything from drilling mud to applications in biogas,
right?
Bioalgae.
I was gonna say any kind of fluid flow, right?
Anywhere you want to optimize heat, So we were just looking at a project the other day where we're using what we've done in modeling of an aircraft, 777, and run it into the side of a nuclear reactor that's being proposed as an anti-terrorist.
Right.
So here you got two different industries. When did you ever think those two would meet? Right. So on this application, through regulatory, people were trying to do certification of integrity through accidents. And so a combination of models and space that really is interesting. In the energy space, we use those same technologies.
Yep.
So I talked to you a little bit earlier about crash testing, which is not eliminated in the auto industry, but greatly reduced. And now they do all of that, and there's some great stuff on YouTube where we do it with Legos for kids. It's really fun to watch.
Oh, that's awesome. I'm gonna have to look at that.
Yeah. We take a Lego Bugatti and run it into the side of a Lego Ferrari, and
my 4-year-old's gonna love that.
Oh yeah, well all these little discrete Legos go flying around,
awesome.
right? And we have the actual in the video. That's quite cool. But that's being used in now in the energy space, because what if I have a hydrogen car on a rail car? What happens when do I have a catastrophic failure? What do I do to contain batteries structurally, right? So in the oil and gas space, we sit with a lot of the sensor development. We do computational fluid dynamics with some of the customers I've talked about before, working with some of the majors to look at what do we do on emissions mitigation.
Right.
So greenhouse gas or methane or flare optimization. Hydrogen embrittlement, right? What are we doing in terms of at the macro? We talked a little bit about materials, macro, micro, and mesoscale to recognize time, temperature, and constituency of hydrogen, how we think this storage tank pipeline.
Right.
Because historically, we're working with the lowest carbon solution out there in oil and gas. Most of the pipelines, 90% of them are low carbon solutions. So bringing these tools to basically simulate any aspect in the energy space. You can just imagine electromagnetics, antenna, even 5G antenna interference out on a rig.
Yeah.
So technologies, as you said earlier, that show up in other industries, show up in this industry for sure, even if we're not the first adopters. We work with a company, this is kind of cool. We work with a Flare. Flare is a Teledyne company to do thermal cameras out on the West Coast. I was out with their CTO a few weeks back, brilliant guy. And their product is being used on cars and trains and planes and offshore because people are able to use that to signal some level of corrosion, actually. And so anyway, long story short, these guys have embedded their application in our libraries. So if you're one of these companies that wants to put a thermal camera in, and they're a market leading technology, you now not only have the physics, but you don't have to go do the simulation. They've already done it for you. And now you can do a systems level integration of that thermal camera into your solution at a much higher level of fidelity.
Without having to do anything from scratch on your own.
Correct. And why should you?
In labs.
Yeah.
No, I think that's the, we've been talking about it since you got here, but the the cross learnings from other industries, especially those like aerospace and automotive and industrial manufacturing, who have incredible standards for these things, who are literally, maybe take automotive out because we all know lots of things on cars are designed to fail after the warranty, but of course they are. For automotive and manufacturing, things are designed to last and be as robust as they possibly can for as long as they possibly can, because that's where all your money ends up. Right? It's all the CapEx spent into that equipment that runs the entire operation that makes you money, which sounds a lot like the oil field, right? Where you've got all this heavy equipment and these remote locations, milling over with no resources and all this stuff. And then it's like, yeah, but they're still doing, non-destructive testing in a lab somewhere without any kind of simulations on it. Or it's like, yay, we've got this new downhole, tool gauge, perf gun, whatever. But we have to go test it in a lab. Yeah. And it's like, why don't you simulate that? Or like, even on a drilling site or a frac site or anything like that, right? Like you have to turn your phones into airplane mode because of the radio interference and stuff with all the charges and stuff on a perf gun. Why aren't we modeling those things? Like if you've got a perf gun that you're worried about, instead of having to do destructive physical testing with that, simulate it.
And I was saying the same thing with wind farms, right? What's electromagnetic interference with radar with wind farms? And so these technologies play across multiple industries, which interestingly enough, I mean, one of the tools that we have is called SCADE. And it was a French acquisition about a decade ago that we made. And they were deep in the French nuclear industry. Now, the French are out there ahead of everybody else in nuclear. They just have been doing it longer, and they have standardized designs, which have made it much safer. Right. And if you get trained in one, you can work on another one. Brilliant idea. We've made them all uniquely different. Right.
Southwest model. Right?
Yeah. It's like the steering wheel this time is in the back. Yep. I mean, so, the training anyway, so that makes it more difficult. So this software company basically had developed certifiable logic that you could tie together, if then kind of control, for very important safety systems, right? Where you want to keep the code clean and simple.
Industrial control system type.
Industrial control system, right? And it is the standard for aerospace uses it, and then the standard for nuclear as well, which is embedded software that we have used this tool for that gives you a certified to standard for that industry code. So after you're done with the kind of the modeling and a bunch of what ifs and optimization and so forth, then it will drop you the certified code. That could be used in any industry, healthcare and so forth and so on. So I think there's some places what happens is, just like the startups that we acquire, they may be focused in one particular industry. We've got this technology that's really cool. You've heard of the DART mission.
Yeah.
Right. And so first time we knocked a celestial body out, Ansys was behind that, a lot of that simulation, right? And that same technology can be applied to the hydrogen car we talked about, that you want to run into the side of or a geothermal drilling device that's going to be coming through and pounding through bedrock. So it's almost limitless what people can do. I think what we see the migration to now is a lot more of that automated workflow, where people are saying, listen, now that we've done this engineering 6 times and we have it in the tool, why are we still doing that one? Why don't we be doing other optimization? So and as far as digital engineering goes, we get into that automation space with our partners. Like you mentioned some of the CAD companies. We're not a CAD company, we're a simulation company. And so that in IoT has made what used to be digital assets that were primarily used for design now fungible enough. Right. Because you're getting real-time data, you can use them to steer your operation. Yep. So you put them out on the edge and you make a reduced order model, and you're collecting real-time data, and you're basically tuning that model to the variables that are unique. Yeah. And what's cool about the oil and gas space, really, what I share back to the folks I talk to in aerospace, so I don't beat up on people that beat up on gases, by zip code, we talked about, the geology is different. Aerospace, 3 miles up is right. 5 miles up, 10 miles up, it gets really simple. I say simple. I'm not saying the systems are simple. Right. The systems and the products are complicated.
There's less variables.
But there's less variables. Yeah. It's more uniform. It behaves more uniformly. You don't have that volatility. So where we should be used in this industry more is in testing the boundaries of the control volume of understanding against the variability. And it might be geoscience, or it might be offshore wind or offshore platforms, right? Yeah. Rogue waves and hydraulics and all this, hydrodynamics and so forth.
Yeah, no, I mean, I remember in undergrad before I graduated, I think it was Halliburton came, or maybe it was BP. Somebody came and gave a presentation or like it wasn't during class, it was just a side thing, but on all the simulation that went into like these floating offshore platform, right? And like a deep water platform, right? Where it's truly floating. You've got, not only is the platform basically just like lunar modular where it's got jets and motors on all sides so that it can stabilize itself, but then you've got the actual pipe coming from the platform down to the ocean floor that has to deal with the waves and the current and all of this stuff. And it was just like, man. And that's the thing that like we always talk about, is just the energy workforce is some of the most technical and like incredible in my mind because of all of the problems that they face, regardless of which side of it is. And yet you still have like, you get all these knobs that get twisted, or what, corporate structures, politics, etc. And then yet we still can't solve some of the most like basic issues with some of the things that we have. And it's like, or like, we're not, there's so much rotating equipment in every industry, but no less oil and gas. Yeah. And it's like, hey, if you're a manufacturer of a compressor, a pump, a turbine, et cetera,
a bearing, a seal.
Yeah, literally, or even the circuit board, like you were talking about, like, why aren't you modeling that? Because everyone tries to optimize for costs, especially when prices are low and all of that stuff. Sure. But it's like, hey, if your equipment can last twice as long because you run all these models and you design it properly, that saves you a ton of money and time, because that's the biggest cost in the oil field is time and money.
Think about electronics in a downhole tool. Right? You've got a bit on the front that's banging
it's
that tool around.
Worst conditions in the world for most of our equipment.
But you have that actuator right there, and you're sensing what's going on in the vibration. Did you take that vibration in the circuit? Did you do the circuit board analysis for the, let's say the resistivity tool or the acoustic tool? Did you do the analysis on that circuit board, temperature, time, vibration,
PVT stuff,
and then has test against it? Nope. Okay. And where did you put it in the tool? Well, we wrapped it in foam. I didn't ask you if you wrapped it in foam. I asked you, where did you put it in the tool? We put it over here because that's where we had room for it. Well, you just put grandma on the end of the diving board. Right. Okay. I mean, so at the end of the day, you see this in design. And I really had the privilege of being in so many different products that as you and I talked about, it just keeps coming back.
Yeah.
Right. It's basic physics in some cases. And why would you not? And the excuse can't be, well, we can't run those systems. No, you can.
Yeah.
You absolutely can. And when you do, and I've seen us do it with customers who say you can't, and very quickly they become adopters. But ultimately, too, it may be because the electrical engineer and the mechanical engineer, he gave me this hole over here to put my stuff in, and that's what I'm going to do. And what do I got to say about it? So, I think when you get all those folks in a room and you have a leader that is willing to let people, and my favorite phrase is, and I just adopted it because I travel all the time, you have the freedom to move around the cabin.
Yeah.
You have got to give engineers and scientists, and I say 10% of their time, not 5, not 2, not after hours, you got to give them time to connect. And if you don't, you're intellectually thwarting that organization, full stop. And people say, you talk with folks and say, well, no, we don't do that. We engineers aren't, they'll fritter their time away. And you look at them and say, why did you hire that person?
Right.
Did you hire them to put fill a hole with a screw, or did you hire these folks to figure out I don't need the hole or the screw? Right. I can use glue.
That's
right?
Anyway. That's absolutely correct. Right. Like at the core, we love to solve problems. It doesn't matter what type of problem it is. Like I will spend an inordinate amount of time trying to solve some random ass problem because I am motivated by solving problems that a normal person would have just quit on. 5 minutes in, right? Like,
you say something there about engineers, which I wrote, and I want to put all scientists in that box too, and doctors and anybody that's curious. But what I've found, and I've had the opportunity to lead companies, commercial folks, sales folks, and I've had CEOs say, "Well, don't you want to go run this business over here?" And I look at them and say, "No."
Yeah.
And they said, "Well, why is that?" I said, "Because I know how to run engineering and science." And the difference in engineering, because I have run those other organizations, is the motivation factor is very different.
Yeah.
Now, I'm not going to say engineers don't want to get paid. And I think sometimes we allow ourselves not to get paid like some of the other folks do. But at the end of the day, the engineering community is a community that can be inspired and motivated and multiplied by the right leadership.
Yep.
And with these tools can be accelerated and multiplied in productivity and capability in terms of what they can go solve.
Right.
Right. And how accurate, how quickly. So to me, what's exciting, what I really enjoy about this company and the kinds of spaces we're in, is it is uniquely engineering and science. And I'm not having a conversation about a sales guy about a spiff or a tiff. Look, I mean, you got to motivate people somehow, right? But bonus on this sell and bonus, that would exhaust me intellectually, right? And so what's kind of all coming, all these kind of things we've been talking about this morning about the oil and gas space, is because we have such a cyclic nature to the hiring and reducing, we beat that culture up big time. It becomes dog eats dog. I'm going to lose my job. I better just do what I'm told, and I better stay in this box. And Bob over there, let's hope he goes before I do. It's not personal, Bob, but I need to.
Well, nobody wants to put their name out there on a project that fails, and then they'll never get another project approved, which is the complete opposite mentality of most other industries. Right. Like, and to your point, a lot of that comes from the cyclical nature of the industry, where it's like, well, there's layoff, prices are bad, layoff just happened, or it's coming, or whatever. And so it's like, I don't want to be the one that gets laid off because I, stepped outside the box and did something trying to be innovative and save us money that costs us some money and then we scrap the project completely because it costs money, even though we didn't see it all the way out to the end to see if there was a different way of doing it, or, whatever. Those are the things, like, I mean, I can't tell you how many times I've been a part of projects where, works at small scale on a well, a pad, a field, whatever. But then the minute they go to try and scale it out across either multiple wells or outside of the field or whatever, there's some nuance and it doesn't work exactly how it worked in the other one. And then they just scrap it all together. And it's like, or we just take like the scientific method and we keep iterating on this thing, right? Like, there's so many things there to it. But John, I mean, that's why I ended up with Ansys, because of the years I spent at GE Research and all these different products at these different companies. There was one common weapon that worked every time. And every leader now, it's a new thing, read a book and say, I embrace failure. I have not met a CEO that the next question you should ask is, to what extent? Right. How big a box can I fail in? $5, $500, $500,000 box? Is it a failure in time? Right. You certainly don't want to hurt people, right? Once you put all those constraints on it, and the engineer who lives by specification sits there and goes, so I can fail if I meet all of that criteria? I don't think so. Yeah. And so what's exciting, and I'll use this example because I think it's a phenomenal example of using computational simulation to basically radically change an industry. And this was aerospace, and it go back about 20 years ago. And everybody, you get on a plane today, you look out, what do you see? You see these little winglets. And those were derived computationally. Yeah. So somebody didn't go out to a 777 and go staple some wooded things on, or even go in a wind tunnel. Well, tell people, for those who don't know, you're talking about the little, at the very
the little vertical winglets
that come up, right? And they're on pretty much every plane.
Every plane,
Tell people, like, I don't remember the stat.
It's 5% reduction in drag,
which is
$10 billion a year in fuel, depending on what the fuel price is, right? And because it's at altitude, and somebody's going to correct me on this, but it's somewhere between 1% and 3% of total greenhouse gas emissions eliminated by that in terms of effect at altitude.
By another foot of material.
5% reduction in drag. Just huge numbers. I was with one of our good cut company called Grundfos, Denmark company, number one in the water pump space. Water pumps are 10% of the world's electricity.
That's insane.
10%, right? Boaters are 45%. They have, in two turns of a dial, and I'm going to say it, but they would say it if you were here. It's because of simulation. I mean, they've simulated at a subcomponent, then they moved that to the system level and so forth, and they're vertically integrated, so they have all the parts and all the assembly, and they've optimized it. And the reality is they've knocked out 80%. Have improved their efficiency 80% in two turns of a dial. And here's a company, 10% of the world's water's electricity. So think about what that is. I mean, you can measure that.
Right.
And, everybody's getting caught in the axle around what new technologies are we going to bring. And that's really important. And we're a part of that. I mean, some of our newest, biggest customers are startups in the energy space. And, they'll be important 2050 or the end of the century for sure. But in the meantime, efficiency is the winner. Half a gigaton of CO2, which is what? 50 gigaton is what we're sitting on. So it's not 10%, but maybe it's given a 1% greenhouse effect on combustion gas turbines, land-based. So 1% improvement in combustion efficiency before you move to hydrogen is half a gigaton estimated across the world. So this is where our tools can be used immediately because we're already with a lot of these companies. They're not focused as much on that. They used to not be as focused on that because it was really just a fuel savings.
Right.
But now they can draw that one level out and get a greenhouse gas emission savings, as you talked about. So you get 2 wins for the dollar.
Well, and that's the other thing too, is it's like, we had that conversation earlier where it's like, oh yeah, it saved 1%, but 1% becomes, at scale. And that's the thing that a lot of people don't like grasp, especially energy across the board, right? You've got extremely expensive, high risk assets that are, like the pricing on those is volatile, like it goes up and down. But then you've got this, like we're seeing it more and more now where you've got this hyper focus on, once things get so expensive, you can start really optimizing those efficiencies on them. Or if there's so much pressure from whatever perspective of the table. And so like I've seen a number of just like waste heat companies spinning up, whether that be waste heat off of a compressor or a pump or whatever that be on site, or a full power plant, right? Like, and that's the crazy part. The physics is the same. Yeah. Right. It's just how much value or efficiency does that bring you, and what does that scale out to be? And so I think that's, to me, like the future of kind of energy is, as we say energy addition, not transition, because that's kind of where we sit. But we all know that the source of energies is going to change over time. But I see the near term, there's all this pressure and focus and incentive now, finally, for people to decarbonize, to reduce emissions, to increase efficiencies. And those are, most people think of things like operational efficiency. So how do we spend less time doing X or whatever, but then they don't think about it down a layer where it's like, okay, what is the efficiency of my motor? What is the, CO2 emissions of that motor? How do I make that my thought is I see the future where near term, we really start gaining a lot of ground on those efficiency metrics.
And we need to. I mean, 65% of the energy produced, converted and or consumed on planet is tossed, right? I mean, just let that soak. Yeah, 65%, and that's only improved 5% in the last 50 years.
Right.
So
you compare that to like the compute efficiencies, right? That you see on the
there's no reason for it other than what you just described, and maybe what's kind of interesting about that is if efficiency is looked at a systems level.
Right.
I used this example the other day with a customer. I said, look, and we were having a nuclear discussion in the UK. And I said, look, here's the problem with not running an integrated systems model of whatever it is. I don't care if it's an offshore rig, whatever it is. If you're bringing equipment in from all of these different OEMs, Cummins, GE, but everybody has to put margin on their components and their systems. And usually they try to get rid of the component level and they put it at the system level. And so if this guy's got 5% of margin and this guy's got 5% and 10% and so forth, and I start to load those into a systems model and I sub-optimized around all of those extra margin, you've padded this thing and it's cost and it's inefficient because you've sized this part thinking he's going to be 5% less power.
Right.
And so you've gone ahead and cut the penny and said, look, I'm going to make sure we don't have an ounce more heat exchange than I need because I didn't do a systems level integration of these assets, right? So I think what I'm seeing is, and this water pump company was a good example of that, is they started with the impeller. That made an improvement, right? And then moved away on. But in materials, which we have an awful lot of software in the material science space, we have a customer I was with in Israel about a month back, just before the fighting started, large printer company. And they have these large drums. And you would think this is low tech. It's not low tech. These are high resolution images and they're printing out thousands of them very quickly. And they sell these machines all over the world. And I'm sitting with a mechanical engineer who points me to this drum, this large metal drum that's spinning. And he says, look, my boss says I need to dematerialize this machine. And so there's 2 pieces there. I want to dematerialize, but I also want to put circularity in so I can recycle, right? But ultimately, he looked at me and said, well, what do you think we can do in terms of reduction of weight? And I'm just looking at the thing spin. It's got to be going at least 1,000 RPM or more. And the machine starts and stops and starts and stops. And I look at it and I said to him, 65%. And he looked at me and said, no way. I said, I'll give you my paycheck for 50% because I'm not going to do the problem myself.
Yeah.
But ultimately, every time we see people go in that have never done a physics kind of that level of analysis at that level, 50%. And you say, okay, that steel that would have had to been shipped Right. That's material that would have had been kilned, mined. And when you start doing the full carbon footprint on 50% material, this is why additive is so exciting, because you're only putting the material where you need it.
Right.
And so when you look at that kind of thing and you see that kind of, I'll call it waste. And I don't want to offend the company because they're a good company.
Yeah.
But that kind of waste on the table, you know why we're at 65%.
Yep.
And we got a long way to go to take the engineering to a level. What people would say is over-engineered. Well, that's way over-engineered. Look at all the metal. That's under-engineered today, right? You don't put more metal in something you don't need to put in more metal.
Right.
Yeah.
It's very true though, right? Like, because historically speaking, as engineers, we're taught factors of safety, and you want to Toyota, right? Yeah. Like Toyota is a huge international brand and major car company because people have faith that it is over-engineered, or they have been historically at least, right? And so like, it's funny because the historical like definition or context of what that means is completely different now than it was even 10 years ago, right?
Absolutely, because what you want to do, if you haven't done the analysis, and we do something as simple as these glasses, and recognize that the hinge is the fail point most often. Sometimes it's these little things, but most times. So if I put more in the hinge and I do that in a calculated way, that's engineered. And that's not over-engineered. That's just engineered properly. If I put more metal anywhere in this and I haven't done the analysis, that's over-engineered or under-engineered, in my opinion. Right. So I'm really screwing up with the terminology on this, but I do think people need to reflect on that. You know, elevators, they can afford a high level of safety, but aircraft can't, frankly. So they have to be engineered because I've got to only afford to lift that metal 5 times a day and drop it back down safely. I can't afford, extra metal.
Right.
And, we were working on a project one time where we were trying to take one fan blade out. It was 65 pounds, and it meant something because you had 2 engines, and that's 120 pounds, which is the weight of an average passenger. Well, not North America anymore.
Yeah.
Anyway. So it's just kind of an interesting thought about how you get to that system.
No, for sure. I think that's like I said, I think and to your point, like there's so much that has changed on the material side. And the manufacturing side of those materials, right? Like printed material, whether that's metal or plastic now, to your point, like not only is there no waste, but then you can put things exactly where they need to be without that incremental cost of, honing it on the like post-manufacturing work, right? Like,
and you see the dance of that laser, the melt pool that it's creating. It's mesmerizing.
Yeah,
actually. Now they have 4 lasers, 5 and 8 lasers working at the same time on some of these machines. But what's interesting is we pre-model that. So we have tools to pre-model every 25,000 print layers for thermal distortion and or or stress that would be induced in the print, so you can optimize the print dance to minimize that thermal stress. People aren't using it.
Yeah.
So they're like, well, additive's too expensive. Well, it's too expensive because you're throwing a lot of stuff away because you're not doing a pre-print analysis and letting the printer decide what orientation to put it at. But we're out. I mean, I'm very bullish. I go on for hours. I won't on additive, but I'll leave it at this. This is where simulation and math are going to be just incredibly important to mature additive. Additive's replacing castings in a lot of ways, right? And we had a machine here at Rankin Road when I was with Baker, when I had the additive team, where we could print 3-4 materials at the same. Now they have 8. So you're essentially able to print your own alloys. Right. And we've been, as Ansys, we've been buying libraries of these alloys from the different aerospace companies like a Siemens and a GE and putting them into our library so people can use them where it's not a competitive threat for those. I mean, it's a commercial agreement. But ultimately, what's really pretty interesting about that is we started printing graded materials. So think about, I remember when I started to design, we had engineers that everything was in 2D. And I just couldn't think in 2D. So I, as a department led, I said, you're all going to go to 3D. I don't want to hear about it. We're not designing in 2D. This half a whole stuff not lining up. We're done with it. And so we started using 3D CAD. This is going way back. But anyway, the point is you're able to optimize that print on a 3-dimensional matrix of material. So you might, like an M&M. I could print it soft in the middle and hard on the outside. And there is no cladding layer. There's no welded layer. There's no joint. And today when we want to change materials, like this cup, we have plastic on the top and paper at the bottom. We make 2 separate parts. So we can do a homogeneous manufacturing. Well, in fact, it's much more efficient in many aerospace applications if I want to combine parts to actually be able to change that alloy to be springy at the bottom or hard at the surface.
Yeah.
And that is going to revolutionize. And that is not going to be done. No engineer is going to be able to think in 3-dimensional material, non-homogeneous.
Material science is already hard enough out of the gate. That was my worst subject in undergrad.
Well, this will mature, and we're partnering with a company called Materialize and a couple of other companies here. We're going to mature this process, and my brain says we got it in less than 5 years, but and maybe it takes a little longer. But ultimately, people are trying to certify every part for NACE or whatever your governing body is in whatever industry you're in. And what we really need to do is certify a smart process.
Yeah.
And because we've got in situ measurement and it's all digital and it's all tied together, there's no reason this machine can't figure out it's screwed up.
Yeah.
Right.
Yeah.
And tune itself for the next print. And there's just no excuse for it. And I think we can get there. Yeah. And I think that's going to revolutionize additive almost overnight as soon as we can get this kind of workflow work. Because today your design engineer is going to optimize this cup on strength, temperature, and so forth, what it might be. He's not optimizing for manufacturing. He might think he is.
Right.
But can you imagine if you had a fit for print part and the machine determined and threw another variable into the optimization routine after one print learning about temperature or time or anything and absolutely optimizing the design again against what would be an optimized print. This is it's fundamentally doable and will be phenomenally powerful.
No, I think that's, we're running out of time, but so we didn't get to talk about it. But that's one of the things I was going to actually ask about with AI in your space, since AI is on everybody's tongue this year. But I've already seen some stuff. I don't remember what it was for or what, but it was essentially that, right? Where they had a part, then they threw it at, they did the model, everything, and then they started essentially letting an AI try and optimize the part by itself.
Generative design.
Right.
Yep.
And it optimized a part that looked completely different. And of course it's got new additive manufacturing and all the new, like, here's the old part that we designed 20 years ago. What would that look like today?
Yeah.
Right. And like the difference is crazy. And then you start getting into the math behind it and like manufacturing time, the costs and all these things.
Yeah.
Like, holy shit. This is, it's going to be crazy.
It is. Like, and in our industry, oil and gas would be a really good candidate for it. And why Baker had been investing in it is because really sometimes you're not selling your product, like your downhole tools, right? And or your wireline tools and our drill bits. We're able to print those in full disclosure. I mean, we disclose that publicly through patents and so forth. But ultimately, the low volume sometimes. Unique alloys. I mean, this is a play,
or just the manufacturing process.
Right? Yeah, the manufacturing. So it's a niche. It's a niche for the oil and gas space for sure. And I found it kind of interesting. I still ask the question because I'm super curious. But I'll ask a company, "Hey, look, do you do anything in additive?" And very quickly they'll come back with an answer that was probably founded 10 years ago.
Yeah.
Well, it's too expensive, or we make too much volume. And I'm thinking, you have no idea what's going on in healthcare right now. I mean, healthcare we're all unique. Our bones are different. Right. I mean, it's just this is going to be revolutionary. It already is revolutionizing healthcare and aerospace. And I think ultimately, oil and gas might be a later adopter, but is going to have fundamentally an opportunity.
Yeah, I mean, it makes a ton of sense, right? Like again, oil and gas. Most of the issues or kind of problems that we run into stem from the materials, right? Like, so there's always salt water. So corrosion and metal are not always the big fans of each other, and they don't work really well over time, and it doesn't help the part and all of that stuff. And then again, you're also moving all of these materials that have, whether it's LNG, CNG, hydrogen, to your point, like that change the way the metallurgy is over time, and also change under pressure and temperature. Like, there's so many little things. But again, it sounds complicated because that's always changing. There's always different states, but it is physics and they fit into a PVP model. They all have their own curves and all this stuff. Yeah. And
somebody modeled that pipeline originally, probably. If it was any kind of service at all, you'd want to model it. And so why wouldn't you now have that not as a digital asset that's, to your point, monitoring all the conditions that are coming over time in that product. And over time, I can then predict, not just disclose where I think I'm going to have a problem, but predict that I'm going to have a corrosion problem 10 years out, 5 years out. So it's how do we kind of use, and IoT investments in the last couple of decades have really advanced that opportunity. I think many people are still in a different paradigm, believing that this stuff doesn't work and we can't do digital. And I was in Europe a couple of weeks back with a large hydro turbine producer, and their customer took our tools, designed and reverse engineered all of the turbines with a third party supplier who did the engineering work to create digital twins on erosion and of their hydro blades based upon rain and silt and all this stuff in the lakes. And they've got 130 hydro plants. And I had a customer tell me, the models don't work. And why are they doing this? Because you have the mindset that the models don't work, and they have the IoT connected. And so they're just creating a digital asset that you should have given them if you wanted to help them get there about a year sooner. But ultimately have found the value in that. So these assets in our energy space, some of them, many of them, dawned well before the dawn of digital, and are being, even nuclear plants around the world are being recast for another 50 years, recertified, whether it's in Paris or the United States. It's the same discussion because we can't afford to have all that base load come off right now. And so, they're using the tools differently than they did in the past. But if you're not sharpening that knife between cuts, you've made a mistake in the engineered world anyway.
No, that's awesome. Yeah. Well, we're out already, which is crazy. I feel like we could sit here and chat all week, or all afternoon. But we'll wrap it up on the speed round. So I'll just pepper you some questions, some short, quick answers. Couple books either on the technology or innovation or product side that you would recommend some people check out.
One of my favorites. There's a lot of talent books. I won't get into a lot of that discussion, but certainly on innovation, one of my favorite ones is actually Fast Innovation. And I was talking to somebody the other day, and he picked one off his desk. And I used to have my staff read it. It was a good combination of Lean, Six Sigma, and design. And everybody out there says, "Oh, he's a GA guy. We're going to hear about Six Sigma again." That's not what I'm going to talk about. But ultimately, it's a means of solving a problem and knowing it's solved. Define, measure, analyze, improve, control. It doesn't get any more straightforward. It's really the scientific method, if you would, with tools and ways to measure your way through. This book does a nice job. It was written by a couple of young ladies here in Texas, I think, in the Dallas area. And it is, I bought, I don't know how many versions of that. That's a great book. The Innovation Dilemma, you mentioned that one. Crossing the Chasm was another good one. One of my favorites, actually, even for engineers, is Jack Stack's Great Game of Business. And this is an old book. This goes back maybe 30 or 40 years. And basically everybody should understand how they tie out to the financials of the company. And so I've talked a lot about innovation and how engineers are underutilized and so forth. At the same time, there's a discipline in the finance community that frankly is useful for engineers to understand, 100%. Right? Because it lets them think for themselves, hey, you wait a minute, I'm going to spend an hour doing this task. What would it save the company if I spent a half an hour doing this task and I did it better or 3 times better? So that Jack Stack's book's really good for that purpose. And there's a number of other good books out there. But I think, my boss just wrote a book on innovation, Prith Banerjee, really, really interesting. He does case studies of different companies that have worked their way through both technology, innovation, and stage gate processes, and kind of going to where you were a little bit, John, about what's worked, what's not worked. And they're really quite a good read. But those are the kinds of things I think today podcasts and YouTube are a real valuable source of data and information and opinions that are testing my own point of view on different things over time and changing it based upon that input.
I think it never ceases to amaze me. It's like, oh, well, whatever. Like, the breaker at my house keeps tripping. Yeah. Google it and find a YouTube video on how to switch it, right? Like, there's literally no reason
it's so much easier
for you to ever not know how to do something if you want to try and do it, right?
And you don't have to necessarily, the way search engines work, we talked about this earlier, you don't have to read the entire body of knowledge on Moby Dick to know that the whale was really big and dangerous. You can get that pretty quick in the title, but anyway.
I was going to ask you, what are some of your favorite, normally it's just your favorite kind of software tools, but I'll ask you, what are some of your favorite Ansys tools on the software side that you are either excited about or see people really turning out really interesting, like valuable results with?
Yeah, boy, that's a hard one for me because it's a whole gamut. I won't take it all the time. What we're doing in optics is pretty exciting because of where optics are going in augmented reality and virtual reality and these, the metaverse. And when you immerse yourself in those environments, we create that physics, right? Water flowing over here, wind blowing over there, and then translate that physics into optics, which is what you and I see. That's really kind of curious and creative and incredible. We've got a number of products that I mentioned, LS Dyna, which I really find. We just had a users conference here in Detroit a few weeks back, and thousands of people there. And that tool being used, we brought it out of Lawrence Livermore Lab. It was originally used as a way of measuring damage on nuclear detonation. And we've, applications over time have developed, and we've used it for this crash test capability, but you can use it for anything. I mean, we used it in this industry recently to look at what would happen if a ship collided into the side of an offshore rig. We've used it to see what would happen if an anchor catches a pipeline. We've used it to see what happens when you drop the reactor. When you're doing a reactor refueling, what happens to the reactor vessel if you, or the containment?
Good thing to model.
Yeah, all kinds of great. So I like that one, and that's the one I talked to you about on YouTube.
Last thing, where can people find you? How do they get in touch with you if they're interested in learning more?
Sure. Well, it's scott.parent@ansys.com, recognizing there'll be some spam today that comes out of that. But ultimately, that's where they can get me. It's
you're on
easy.
LinkedIn too.
And I'm on LinkedIn, and I'm much more customer focused than I've been in any job I've had before. I spend all my time with customers. So I treat anybody that calls me as a customer.
Awesome.
Yeah.
Scott, I appreciate it, man. This has been a ton of fun.
Great.
Excited to have you back. Guys, if you like this episode or any other ones, please give us a review, give us a like, subscribe. Scott, thanks again, man. Appreciate it.
Give us a like. I mean,
go check out
my
Ansys.
Emotional fragility. I got to have the thumbs. I got to tell you, John, I have a stuffed thumb that I use, because when the thumbs, all you could do was give thumbs up, and I would be in these telepresents, and I'm a nice guy. I like to have a lot of fun. So I have a foam thumb that I can go this way with too. And it always gets a laugh, and yet you're still sending a message. But ultimately, it's a thumbs up on this. I enjoyed my time with you. A lot of fun.
That's a good tool. I like that. Appreciate it. And everybody out there that's manufacturing stuff, please talk to these guys, because we all know that our stuff could last longer and be better designed. So appreciate everybody. Christmas is in a little over a week away. So I'll also say Merry Christmas and Happy Holidays, everybody. And we'll see y'all after the break. Thanks.